All right, so we're going to talk a little bit of rational functions. Rational functions are really important in calculus. We use them very often, and when students don't really understand rational functions, a lot of difficulties ensue when we start to talk about limits, especially. So a standard form of a rational function. And so I'm just going to call my rational function r of x. So I'm going to write p of x over q of x. All right, and in this form, p of x is a polynomial. Remember, a polynomial could be just a constant, right? It could be 3. That's a polynomial. And q is also a polynomial. So basically, a rational function is a polynomial divided by another polynomial. Right, so let's start off with the most basic type of rational function, which is 1 divided by x, sometimes called the reciprocal function. Right, so if I look at this function, right, f of x is 1 divided by x, first thing that I always want to do with rational functions is find any type of domain restrictions. Right, so if we think about what f of x equals 1 over x means, well, if I pick any value of x, like 7, right, so if x equals 7, then I just get 1/7, right? So it represents a fraction. If I say x is -2, I get 1 over -2, -1/2, I get a fraction. If I say the square root of 2, I get 1 divided by the square root of 2, I get a fraction. So what these rational functions really mean is, hey, we have fractions when we plug in x. So since this is a fraction, right, we just want to think to ourselves, what can I never divide by? What can I never have in the denominator of a fraction? And you probably know the answer is 0, right? So my domain is going to be all real numbers except 0. There's going to be a lot of different ways that we could write this. If we were doing it in interval notation, we would say negative, we'd get negative infinity to 0, u for union, 0 to infinity. The way that I will write it a lot, just because, I don't know, I do this math thing and I like to be a little bit more precise. I like to be a little bit more kind of like, well, concise, I think I already said that. So I would say that x is an element of the real numbers. The little slash means except x is 0. Right? So this is another way of writing. The domain is all real numbers except for 0. All three of these things are fine. Right, so in terms of our range, right, so we'll see in a moment that the range of this function is also going to be all real numbers except 0. So this is also why I like this notation a little bit better. It kind of gives a little bit more of an idea, right? If I say y is an element of the real numbers, except for y is equal to 0, you can tell now I'm talking about y's instead of r's, right? I could say that my range is also this right here. But if you just kind of come across that interval notation, you have no idea if I'm talking about the x's or the y's or anything like that, right? So kind of like this notation is a little bit better. So if I just kind of wrote out what this thing is, as you can throw this into like Desmos or something else if you really wanted to, but we'll see why it should look like this in a bit. It's going to look like this. And we're going to have the exact same thing kind of reflected over this origin. All right, so this is what our function's going to be. So we would see that we can't have x is equal to 0. So this is, in this particular function, a restriction. Can't have that. And this particular function is also never going to hit the x-axis, right? So this is why our range is going to be all real numbers except for 0, right? We never hit the y-axis, right? Put another way, if I say f of x equals 1 over x, and I try to say, hey, when is this equal to 0? If I solve this equation by multiplying both sides by x, I get 0 is equal to 1, which just never happens, right? There's no way that I can make that equation true. Just another reason that we never have an x-intercept. So in general, when we have a rational function, our domain is going to be all real numbers except values of x, which make the denominator equal to 0. Then once we kind of find those values, right, these are what we call the domain restrictions. There are two different types of restrictions that could pop up. We either have a vertical asymptote or we have a hole. We don't really do a ton with holes in like pre-calculus, but in calculus, they really pop up as an important kind of learning point because they help us with kind of like understanding how limits exist around some little value of x. So a vertical asymptote occurs when we have a factor that can equal 0 left in the denominator after simplifying. I should have given you more room for that one. And a whole is going to occur when we have a factor that can equal 0 that cancels completely out of the denominator. And we'll see kind of an example of that on the next page. So these are just our definitions that we care about. We can also find these horizontal asymptotes by thinking about end behavior. You may remember from like pre-calculus, also like oblique or slant asymptotes. We don't really care about those a ton in calculus. So like in my calculus courses, there's never a time where I'm like, let's find what the slant asymptote is. Like, who cares what it is? So to graph rational functions, here's like the laundry list of steps that we're going to follow. We're going to kind of like do some work, but ideally I want us to understand kind of conceptually where each of these kind of steps comes in play and how to apply them. So I'm going to do some examples of this on the next page. So this is just kind of video 1 for